how they map onto the architecture of the computer. And in specific, recently we looked at if statements and saw how the if statement could be realized with the instructions on the computer by implementing a test for the if statement by inverting the logic of what you write down in your high-level language and doing sort of the opposite of that in our compare instruction, and jumping around the then part of the if statement, if that is true. So if the opposite of what you wrote down is true, we don't want to do the then, so we jump around it to the else part. And at the bottom of the then part, we then have an unconditional branch down to past the else part. So that little template can implement an if statement for any if statement. And it's a little confusing because in the assembly language, you're looking at a test that's the opposite of what you wrote down. And then the compare instruction itself is a little confusing because it looks like the operands are in the backwards order from what you're really trying to express. So those two opportunities for confusion notwithstanding, hopefully everybody sees how the compiler can always use that form in emitting the code to realize an if statement on the computer. So now we want to look at some other high-level language constructs that we use routinely and how they're realized on the computer. So we'll look at various forms of loops. So the first one we look at is a thing in C called a do-while loop. We have two flavors really of while loops in C. The do-while in C does a body of code, and then it does a test at the bottom. And if this test is true, it goes back up to the top and does the body again. And it just keeps cycling through the body until the test is false, in which case it drops out of the loop. Now, in reality, if you look at a programming language theory book, the terms that they will use for this kind of a loop is you'll see it referred to as a repeat until, because the body of the loop always executes at least once because the test is at the bottom. So you're repeating this body. And the until is, of course, the opposite of the condition you would write with a do while in the C formulation of it. So if you look at languages like Pascal and Ada and all those kind of languages, they have repeat until, which is really more descriptive of what this is supposed to be doing. But in C, we have this do while. Now, if we sort of transliterate this control construct into a go-to form, just to sort of mimic what's going to happen in the assembly language, we'd have a label, then we'd have the body of the loop, and then we'd at the bottom have our test, which we could realize as an if statement. And if the X is true, we'd jump back up to the top of the loop. So that would implement this in a sort of go-to-ish form, which you then could see how you could translate onto the instructions on the computer. So what does this thing do? What does pcount do accomplish? So we're going to return an integer, which is the count of the number of 1 bits in this unsigned number that was passed in. So how does it accomplish that? Well, we start out by setting the result, the thing we're going to return, to 0. And then we do this loop. And what the loop says is result plus X ended with the rightmost one bit turned on and everything else zeros. So we line up this rightmost one bit and we AND it with what got passed in, and the result of that is either going to be 0 or 1, depending on whether that rightmost bit of X is a 1 or a 0, right? So this produces either a 1 or a 0, and if it produces a 1, we're going to add it into the result. If it produces a 0, we'll add 0 into the result. Then we shift X, the thing that got passed in, right one position. So X is equal to X shifted right one position, which marches the rightmost bit off into the bit bucket and shifts everything else over. So then if the X results from that shift is all zeros, then we quit. But if there are some 1 bits left in X, we go back to the top of the loop, and now we look at the new rightmost bit and add a 1 in if it's a 1, and we shift it. We just keep marching X across, looking at the rightmost bit and adding a 1 in anytime it's a 1. But the slick part is, of course, when you march the last 1 off, suppose you had like 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1 or something, when that very last 1 marches off into the bit bucket and you're left with nothing but zeros, then you get to quit. So you don't have to look at every bit position, right? You just look at all the ones until all the ones have been marched off into the bit bucket, and then you can quit. So that's how this works, right? Everybody see how we count up all the ones that are flipped on by doing that. So then we look at realizing it in assembly language. If we took our little go-to-ish version of it, you know, with the test going up to the loop, and just translate that directly one for one into some sort of assembly language, we have something like this. They're saying somehow magically the X variable that got passed in put into the EDX register. And we're going to use the contents of the ECX register for our result as we run this code. So we move 0 to ECX. That's this business here of initializing result to 0. And then here's the top of the loop, this label 2. When a compiler takes your code and it needs to generate labels, it just generates label 1, label 2, label 3, label 4. Every time it needs one, it just gets a new label. And so they have these totally nonsensical names like .L2, .L3, .L4. So we have a comment in the assembly language where we've manually put in a comment saying, oh, this is our loop at the top there. So now we're going to move EDX, which contains X, into EAX, and then we're going to AND, long word, constant 1 with EAX. So the result of doing that is either going to be to have a 1 in EAX or a 0 in EAX. And then we're going to add that 0 or 1 to ECX, where we're accumulating up the result. And now we do a shift right logical of the X. That's just this business here. And why is it a logical, not an arithmetic? Well, we don't want to, if the leftmost bit happened to be a 1, we don't want to propagate that 1 all the way across, right? We'd never terminate the loop if we did that. It'd just keep going forever. So we only want to count the ones that were there when X showed up, right? So we want to pump in zeros on the left when we shift it. So that's a shift right logical, not a shift right arithmetic. And then we do a jump not equal. Well, not equal what? When it says not equal, it means not equal 0, right? So when you did this shift of that X, did the 0 flag get flipped on? If the result of this instruction produced a 0 in that register, the 0 flag would be flipped on in the condition codes. And so we jump not equal if that condition code bit is not on back up to here. So hopefully you see how the assembly language implements this, counting up how many 1 bits were in the thing that got passed in. Any questions about that? So if not, we move on. And so if we're thinking about the compiler, when it sees these do while loops spitting out a template of code, it could always look like this, right? A do, and then some body, and then a while, and a test sort of translates into having a label to jump to the body of the code, and then the test down there, and then go to, if the test is true, back up to the label. And we're interpreting in C, of course, 0 is false and anything else is true. So this test really is saying, does this expression, whatever the test is, produce the value 0, in which case you fall through. Otherwise, you're going to take the loop, which is directly reflected in that jump not equal back to the top, right? Okay. So this little template, however many statements you happen to have in the body, could be 4,000 statements in there, it doesn't matter. But the compiler can wrap that around with this structure and create the effect of that do while loop, which is exactly what the compiler is doing. So now we look at another flavor of while loop that you have in C. And this one is the actual one that is referred to as a while loop in the programming language theory books, right? Not a repeat until structure. So the while loop does the test at the beginning before the body of the loop, whereas in the do while we saw previously, it did the test after having executed the body once. So we may never execute the body at all in a while loop, right? If this thing is false when we first get here, we don't do the loop at all. And we just keep doing the loop until that test is false, in which case we want to terminate, finish the loop. Well, if you do that in your go-to version, what would it look like? Well, it kind of looks like the thing we had before, the do while, but it's got this test stuck on the front of it that says, is the opposite of this test true? And if so, jump down to done and don't do the body of the loop at all. So that is like the test happening first, right? But once you do that, then the rest of it kind of looks like the do while, right? You do the body, you do some test, you go back to the top, you do the body. So that looks exactly like the do while, but the while has this test at the beginning before you hit the loop, meaning you may never do the body of the loop at all. So we can kind of build this one out of the one we already had, right? But it's not equivalent to the do while because you may never do the body at all, right? Questions about that? Okay. So if we look at the code for what's going on here, let's look at how it works. It's got the same thing in there. It's got result is result plus X ANDed with 1. And then you march X over to the right and drop the rightmost bit off the bit bucket, and you go back. And so when it hits 0 up here, that's when you'll finish, right? So it will terminate after all the bits that are ones have been marched off into the bit bucket. But it may never do the body at all if the thing you passed in here was 0, right, to begin with. It would just return the result as 0 without even doing the body. Whereas our do while incarnation of this would have tested the rightmost bit for found that it was 0, added 0 to result, and then done the test. So we would have done the body at least once in the do while version. Okay, so that's the difference between the two. So if we look at this, we can take the while test body and then turn it into a if not the test, jump around the whole mess, and then do a do while. So that becomes equivalent. And if we take that and turn it into the go to-ish kind of incarnation of it, then you've got this business. If not test, go to done, loop, body, if test, go to loop, which implements your while loop for you. So now we want to look at a for loop. This is something that we have to do all the time. You want to walk across all the elements of an array or something, you know. So you're going to have iterative loops, loops that count, right? So in C, the for loop is a little bit strange, like a lot of things in C. The way a for loop looks in C is you write the word for, and then you have a set of parentheses, and then you put three things inside the parentheses separated by colons. And the first thing you put in there is the initial statement you want to have happen before the for loop even starts, right? The second thing you put in there is the test, which essentially is the same kind of a test you would have in a while loop, because if the test is false, you never do the body of the loop, right? So in that sense, it's kind of like a while loop. And then you have something you want to have happen at the bottom of the body before you come back up and do the test again. So the canonical version of this, when you're incrementing across a range of values in C, would be to start some variable out at 0 and then test if that variable is less than some size, and then to increment the variable. So it just counts across the loop. Now this makes sense because, you know, if we have an array in C, the subscripts always start at 0. If you put the declared size of the array there, then while that thing is less than that size, you know, your subscript never gets up to that value, gets up to 1 less than that value, right? That you're going to use to index into the array. So that looks like a canonical C for loop started at 0 while it's less than the size of an array. In this case, it's not an array, it's the size of a number of bits we have in a word, and count, increment across there. We got this W size from taking the size of an int, which always gives you the number of bytes that it takes to hold a type that you hand it. And we multiplied it by 8 to get the number of bits. So we have the number of bits here. So how does the for loop work? Well, it's a little different from the way our while loops worked. Now, rather than marching X across into the bit bucket to the right, we're going to take this 1 and we're going to shift it left I positions. So the first time through, shift it no positions, 0. So we're aligning the 1 under a certain bit. And then we do the same thing. We say, is X ANDed with the mask not equal to 0? So if you had a 1 in that position where you're lined up the thing, you'd get 1 for this expression. That would not equal to 0. Well, that's a logical expression, right? The result, the whole right-hand side, is the result of this logical expression. Logical expressions in C always return either a 0 or a 1. So if the thing was a 1 bit, you're going to return a 1, which means you're going to add 1 to the result. If there was a 0 in that bit position, you're going to return a 0, and you're going to add 0 to the result. But then we go back up there, and if we now we take the I and we increment it, so we move this 1 aligned over underneath the 1 bit, and then eventually in the 2, the 3, and the 4, we just march the 1 across underneath the bits of the X, right? and we look at every one of them, and we add in either a 0 or 1 based on whether that position was a 0 or a 1 in the thing we're marching it underneath. So this for loop, unlike the while loop, is always going to march that 1 across through all the possible positions, all 32 of them, right? Going from 0 to 31 shift, right? It's not going to terminate when we've seen the leftmost 1 in X, like the while did with that magic property that, oh, as soon as the thing turned into 0, we magically quit. This one's going to go through all of them, right? Possibly doing more work. And we're shifting the thing in the mask over rather than shifting the X over. So this does the same thing, comes up with the same number, but it may go through the loop more times than the while version had to do it, right? Now, another thing you have to realize about the for loop in C is that you just think of it as a template, right? These 3 things that you give it here don't necessarily have to have anything in the world to do with each other. And you can leave any and all of them out. So you just think of it as a template form that does this piece here, the initial thing, before the first test. Then it does the test. Then it does the body of the loop. Then it does whatever this statement is at the bottom, and then it comes and does the test again. You can put anything you want in there. It doesn't have to count. In a lot of languages, the for loop looks like a syntax of for I equal 1 to 10. Well, the only thing you can do with that is count from 1 to 10. It's an iterative structure, which is kind of what a for loop should be. That's what it sort of means in your brain when you think of a for loop, right? But in C, a for loop can count if you structure it like this, but suppose you left all 3 of those out and just put 2 semicolons in. Well, what do you have now? Well, you could put a 1 in the middle there. You could have semicolon 1, semicolon. And now you have an infinite loop. It just keeps going forever because 1 is always going to be true. So you get the idea that in C, it's kind of a template sort of thing where do this, then do the test, do the body, then do this thing on the right, then do the test again. But they don't necessarily have to create something that counts across a range of values.
Yeah.
You can use it for whatever strange thing you can dream up. It's just to think of it as a template, right? Any questions about that? Okay, so if we look at the for loop as this template kind of mentality, we have this initial condition, we have the test, we have the update, and we have the body. And then we can think of it as, well, do the initial thing, then do a while loop on that test, stick the update after the body in the while loop, and that is a for loop. But this is just such a common thing, right? Where you want to walk across some array and count. So we just have a shorthand sort of way of doing that without having to write all this stuff down out of a while loop. So it's completely, superfluous really to have a for loop in the language. We could get it if we had a while loop by just doing all those things ourselves. But it's so common that we want it. So this way of thinking, take your for loop, turn it into the while incarnation of it. Now take your while loop, turn it into the do while version of that with the go-tos. And then you get this business here as the sort of template that you're thinking about for a for loop. Do the initial test, and then you have a test that says if the opposite of that test is true, jump around the whole mess. Don't do any of the body. Otherwise, do the body, do the update, do the test, jump back up there. Do the body, do the update, do the test, jump back up there. So that's really what a for loop is. If you wanted to take that, then you could just one for one turn that into assembly language statements, right, to create the behavior of that guy. So in our case, if we did that, we'd end up with this stuff over here in our sort of pigeon do while transliteration of what a for loop looks like. But we know that since we just put 0 into I, we really don't need to do this test if not I less than W, right? Because we know I is less than W size because we just stuck a 0 in the dang thing. So you really could optimize out this test in this case because of the fact that we just initialized that thing to 0. Then the body, then the update, then jump back up to the top of the loop if this test is true, right? So any questions about do while, and for loop constructs and how they map onto the computer and actually get implemented and executed on the computer? So notice there's a conditional branch down at the bottom of all those loops, right? Either going back to the top of the loop or falling through to terminate the loop, right? Well, Mitch, I think you can probably look in the index as good as I can in the book and see what section is discussing this. It's in chapter 3. So any questions about those loops? If not, we move on to our next control construct, the switch statement. Now, C originally started out as this little teeny language, and then over a period of many years, it has evolved and added more and more things into it to become what you think of these days as the C language. And so along the evolutionary path there, they would look around at what was going on in these other languages and they would go, oh, that's a cool idea. Let's steal that from that other language over there and incorporate a version of that into C. And so that's exactly what happened with the switch statement here. There was a language called Algol W, and the W as in Nicholas Wirth W, which was a successor, his suggestion for the successor to the Algol 60 language as kind of a competitor to the official successor, which was Algol 68. And then after, well, in this Algol W language, he put a thing in it called a case statement. And then the case statement showed up in, pretty much all subsequent languages, Pascal, Ada, all down the Algol family tree. So C sort of looked around at Algol W and Pascal and those languages and said, oh, well, we need to stuff a thing to do a case statement in our language too. But it's as if there was an unwritten rule when the people that were putting things in C would go to these other languages and steal things out of them, that you had to kind of screw it up somehow in certain ways and make it a little wonky when you took it and stole it out of this and put it into C. So everything they stole, they kind of mangled around in a weird sort of way. And that certainly is true of the switch statement. In the original case statement that this is derived from, you would write the word case up here, and then you'd give it a variable or an expression that produced a value there. And then you'd just write all the alternatives, but you wouldn't write the word case, right? So C, when they stole it, they said, oh, well, we're going to, instead of write case here, we're going to write the word switch. And then for each of the individual cases, we'll repeat this word case, which is just a lot of typing. And the reason they're doing that is so when the compiler sees this word case C, you don't have set braces around that. If they didn't put that case word in there, they could have made the syntax where you just didn't put the case, you put the one colon, and then have a compound statement with the set braces, and then you'd have the two and then a compound statement. So rather than putting the endless set braces, they made the syntax where you put this word case, and then you just list a bunch of junk, and then you put the word case. You list a bunch of junk, and you put the word case. So that's the syntax they came up with in C. And so what the idea of a switch or a case statement is the value of this expression here, which in most languages has to be something that evaluates to an integer, um, positive integer in most languages. There are many languages that are much more flexible than that. But in C, this thing is going to be a positive integer, and you're going to put a value for if the value of that thing is 1, if the value of that thing is 2, you want to do this code. If the value of it is 3, you want to do this code, et cetera, et cetera. If it's none of the ones that you list, then you have a default, which is what you do if it's not any of the ones that you listed there. But you see a couple of weird things about the way they implemented the switch statement in C. One of them is if you look at the case 5 and 6 down there, well, you see that 5 doesn't have a body, right? It just falls through into the 6. And so 5 and 6 do the same thing. Well, the reason for that is in C, you don't have an ellipsis, a dot dot, like you have in a lot of languages where you specify a range of values. That doesn't exist in C. So you can't write 5 dot dot 6 like you would in Pascal or Ada or whatever, saying, oh, for this range of values, I want this deal. So the way you get that effect of 5 dot dot 6 is you write 5 and then you write the case for 6 underneath it. And so if it comes to 5, it just falls into the 6 and does those. Well, that means you need to have this concept of falling through in order to be able to get the effect of the ellipsis in other languages. So what if you don't want to fall through in all these normal situations? Well, then you're going to have a thing called break. So it says, if you come here and you do this, then I want you to break, which means get out of the whole switch statement, right? So one could think that, okay, when they stole the case statement and they put it in C, the fact they didn't have the ellipsis and they wanted to get this sort of thing meant that they had to put this break thing in, right? And then people go, well, that's kind of a pain because now the normal case is I want to do the break most always, right? But then they got something like this. Notice what's going on in case 2 and case 3. They didn't put the break at the bottom of the case 2. So if you came here and the value of x was 2, it would come here and do this statement. Then it would fall through because it doesn't have a break, and it'd do the stuff that's in the case 3, and then it would get out. So case 2 does some stuff, and then he also does the stuff that 3 does. If it's 3, he just does this stuff. So they go, aha, it's a feature, right? So it's kind of like, well, we painted ourselves in the corner. We didn't have an ellipsis, so we had to have that, which meant we had to have break. Oh, well, now that we have break, we'll kind of do some revisionist history and claim we did that on purpose so we can do this combination strange stuff that you couldn't do if you didn't have the break thing. So you can analyze their thinking in the language design as to whether they got here because they painted themselves in a corner without having ellipses, or whether they really did it so that you can get these combination things that you couldn't do if you didn't have the brake. So in any event, you see how it works, right? You got, if it's case one, it does this and it gets out of here. Case two, it does that, falls into there and does that, and then it gets out of there. If it's 5 or 6, it's going to do this business. If it's none of those, like if it's 4, see, we didn't list 4 anywhere, right? If it's 4, it would do the default. If it's 0, it would do the default. If it's anything bigger than 6, it would do the default, right? So you see how that works? So that's the crazy switch statement in C. So how do you realize that on the computer? Well, one way to do it, there's many other ways, several other ways you could do it, but this is one way you could do it, is to use what we call a jump table. So if we have this table, like an array, right, laying in memory, and what we're going to put in the table is the address of some blocks of code that correspond to these blocks that are in the cases of the switch statement. And then what we're going to do is we take this X and use it as a subscript into this table, pick up that address and jump to the block of code that you want to execute based on the value of X, right? So you see how a jump table could implement getting to these different blocks based on the value of X by putting those blocks in memory, having the address of where they live, putting the addresses in the table, subscripting in to get the address and jumping to the code. So if you wanted to write that as some sort of little mimicking it in some C notation, it might look something like the target, the address that I'm getting out of the jump table is equal to subscript into the jump table by hex. You've got the address now, and then I'm going to do a go to dereference the address, right? So that's kind of mimicking in this what this would look like. But of course, it's assembly language. It's not this stuff, right? So you see how the jump table works. Well, there's a couple of little things you have to deal with because of this. Don't put the brake in, fall through to another case, that kind of thing. You got to deal with to implement the jump table stuff to truly reflect the C behavior. So we look at this code that's implementing this little switch example. Would you pass in these 3 longs and we're going to return a long back out? And we got the switch based on this long value here. And we're doing 32-bit code because you see the little 2-step at the beginning of the function, pushing the base pointer, moving the current now stack pointer into the base pointer, and then accessing the parameters that are being passed in by going back up the stack the appropriate amount off of where the base pointer is pointing to get the parameters. So we go 8 back, we're getting X this long, right? And then we've got to compare longward the constant 6 with what we got for the X, right? And this is jump above to L2, which is way down at the bottom, get me out of everything that has to do with the switch statement. Because remember, we didn't have anything above 6 listed in our cases in the switch statement. So the jump above is the unsigned counterpart of a jump greater than. Jump greater than is when you're dealing with things that you're treating as signed numbers, right? But here we're treating this thing as an unsigned number. And we're going to do a jump above to L2, right? If we didn't jump around the whole switch statement, we want to jump to, and this thing here is expressing L7 is a label where our jump table is laying in memory. And so whatever that address is what that label represents, is that address in memory where the table starts. We want to add to that 4 times what's in the EAX. EAX is our X, right? Addresses in the table take up 4 bytes. It's a 32-bit computer in this case. So 4 times the value that's in the X is how far beyond where the table starts we need to go to pick up the address out of the jump table, and then we're dereferencing in that and jumping to that address, right? So that's implementing this business here. Go into the jump table, get the entry at the X offset into the jump table, pick that address up, and then jump to that address, right? To get to the body of the code corresponding to that entry in the jump table. So hopefully that makes sense to you. So that's pretty much the structure of what's going to go on, but we have to account for these little screwy no breaks and fall throughs and that stuff. So how do we do that? We'll get to that in a minute. So this is just illustrating that this jump table is just laying in memory, right, at these addresses. And these are labels, which represent the labels where the blocks of code are, the bodies of the various cases. That's the address where that block of code is. That's the address where this block of code is. Well, you notice one thing that, in implementing the case as a jump table, one sort of downside to that, right? We have out for 0, right, off of the beginning of the table. We didn't have a 0 in our list. Remember, we only had 1, 2, 3, 5, and 6 listed there. But we got to put the 0 entry in, which is going to L2, which is the same place you do to get around the whole switch statement, where don't do it at all, right? So we had to put that in at the 0 position, but we also had to repeat in there at the L2 down here at 4. We didn't have a 4 listed in our cases in our switch statement, but since we're using a table, right, if they gave us 4 to get to the default case down at the bottom, the L2, we had to put an entry in there for 4. You have to account for every value of the subscript. So that's the disadvantage of using the jump table. You're going to have stuff in there, for ones you didn't even have in your list, but they have to be accounted for to get to the default, right? And then 5 and 6, there's how you implement that, right? Those were the ones that 5 didn't have a body, it just fell into the 6. So we have this one label for the body of the code for 6 that goes to the same place. It's repeated in the table, right? So hopefully that makes some kind of sense. All right. So that accounts for missing cases and getting to the default. The greater than 6 gets you to the default by this compare here, right? So then we know it's within the range 0 to 6. So we got to account for 0 to 6 in our jump table. The only other thing we haven't accounted for at this point is the screwy thing that's going on with the 2 and the 3, right? Where after you finish the 2, you also need to do the body of 3 because there's no break there. All right. We'll account for that in a minute. So you see how this jump table works, right? The align 4 is saying that this table needs to start at an address that's divisible by 4. And we'll see a bunch of things about alignment constraints that we have on the computer that we should adhere to later on. But that's just saying there's a 4-byte address laying in the table here, right? And we're going to align the beginning of the table at a address divisible by 4. So each of them ends up being divisible by 4. The read-only data is what that stands for. And that's saying this thing, this table, should be stuck into the memory segment when we're building up in the linker the pieces of the program that we'll explain later into the segment of memory that we're going to designate as read-only data. So it's in there, but can't be clobbered by your program. Okay. All right. So we have a direct jump, jumping around to the default case if it's out of range, and then we have the jump table accounting for everything that's within the range of things listed, right? So here's what it looks like relating back to the cases of the switch statement. Case 1, right? If we subscript in here by 1, we pick up this address, and that would be where the body of the code is for that. Case 2 would be this guy, and he needs to arrange somehow to fall through into this body of the code for case 3. So that's pretty much it, except for we haven't accounted for the fall through business here, and we have accounted for that one just by putting the same label in there. They just do that. But this one's weird because case 2 does this and that, right? So we got to figure out how to make that happen. Well, that's how you do it, right? So we have the little block of code that we're referring to as merge, right? So case 3 jumps down to the merge code, and case 2 does his thing and then falls through into the merge. And so that's how we are accounting for that thing in the case statement there. So we have, if we had some assembly language, sitting there for each of the blocks of code at these labels that are these labels are the addresses that are in the jump table, right? So the default is this L2 that we're going to, right? And then L8 represents some address below all of this junk you're out of the switch statement, right? So anyways, so if we had this business here representing the case for the 3 case, and this would be representing the case for the 2 case, then that shows that we're doing both of them in the case of the 3. That's what that's trying to show too, like this. Case 2 does this rot, which is the label 4. He could have picked some better labels. You have to remember that case 2 is at label 4. So anyways, it does all that junk, and then it falls through into the code that represents the case 3 business, this thing here, right? And then it goes out of the whole switch statement. Case 6 is that guy, which is that code there, right? And he's at the very bottom, so we'd have like the default case would occur after him. It's not showing the branch to get out of here. So in any event, at the bottom of the thing where the L8 label is after the switch, to implement our function, we do our pop BP, a return business, and all that you're doing should have left there it is, should have left the W, which is what's being returned here, should have left that in the EAX register, right, to return it. So each of these blocks of code the compiler would set up so that the W, when it's computing these things, would be dumped into the EAX register. So when you get through the whole mess, the EAX register has the return value in it. Right? Questions about how to realize a case statement on the computer. Now, the downside of doing the jump table, right, is what if I had case one, case two, case three, case 5046, case 9027, default. Well, how many entries would I have to have in my jump table? Whatever the lowest, whatever the 0 to the highest thing I had in there, 9047. But see, most of the entries are going to be the same thing. They're just pointing at the default case, right? So I'd have to have this humongous jump table to handle like a handful, 4 or 5 things that I really wanted to do other than the default. So the compilers actually look at your switch statement and see what the density of these things is over the range. And then they will implement the switch statement either as a jump table or possibly not, just implementing it as a bunch of if statements, right? You can obviously see how you could rewrite this case as a bunch of if statements. If the thing's equal to 1, I want to do this. Else, if the thing's equal to 2, I want to do this. Else, you'd have to, this one gets a little screwy. You'd have to repeat the code or put it in a procedure block and call it or something to get that effect. But you could still do it with if statements, right? If it's 5 or 6, I want to do this code, right? Else, and the else at the bottom would do the default for you. So you could implement a bunch of cascading if statements to pull that off. The advantage of that is in the sparse case where it goes from 1 to 9050 here and you only have 4 or 5 cases, you don't have this humongous jump table. But the disadvantage of the if statement thing is it has to kind of ripple through all the tests, right? If it ends up being the one at the bottom, you got to go through all these other ifs to get to that one, right? So they both have their Achilles heel. The if statement, marches across all the values, testing them until you hit the one that it matches. The jump table is good if you have a relatively small and dense range of values, but really stinks if you have a small set of values over a huge range, and then you got a lot of blank or repeated entries that just point to the default in the jump table. Does everybody see the difference? So some compilers in really fancy languages actually know how to implement a hash function for some of these things, so they get even fancier. So are there any questions about any of this or anything else before we wrap up for today? You've got a really busy week. You got 3 balls that you're juggling in the air. No, they don't have to go from 1. They can start wherever you want. But if you implement it with a jump table, it always has to have entries in it that start from 0 up to the highest number that you have in the set of cases. No, they don't have to be sequential. They do have to be a thing that behaves ultimately like an unsigned number, unsigned positive number, right? In C. In other languages, there's different rules for this. So you got 3 things to juggle at the same time this week. So it's a busy week. Yep. It's busy, but there's a lot of stuff in this course that we have to cover. And so that's just the nature of the beast. So good luck, get busy, get it all off your back. Work hard during the week. So if there's no more questions, but remember office hours are at 1 on Wednesdays, not at 2. So maybe I see you there. Maybe I see you tomorrow. Good luck.